All right, so just to reiterate, equilibrium, it's where those rates of opposing, those opposing would be the forward versus the reverse. Okay, they're equal. So what that means is your products are being formed at the same rate that your reactants are being reformed. So their concentrations are going to be equal. Okay, and we're going to get into this here today. Writing these things called equilibrium expressions. All right, or equilibrium constant expressions is what more accurately they are defined as. So dynamic state. Okay, this term called a dynamic state is where reactions are continuously, constantly happening. All right, they're not stopping. So that forward and reverse reaction that we've been looking at this week with potential energy diagrams and whatnot, and even acid-base chemistry in our last unit, all right, they're constantly happening. They're going forward and they're going backward. Okay, so we've got to identify, well, which reaction is going to be favored. Okay, is it the forward reaction or is it that reverse reaction? And to do that, we use what's called an equilibrium constant. All right, and how do we write that? It's the concentration of our products over the concentration of our reactants. And that's what we see right here. So K, sometimes you may see K as KEQ or KC. Means the same thing. Okay, just like C when we were dealing with thermochemistry, that specific heat, whether it was a capital C or a lowercase c, whether it was a capital Q or a lowercase q, right, they meant the same thing. Same thing here. All right, so don't get confused with that. Now, what do you see around that word products in this? What do brackets mean, Dallas? Anybody? What do brackets mean?
They can't be negative.
Concentration. Those are absolute values. All right, good guess, though. Concentration, guys. So it's talking about a concentration of something. All right. So when we take a look here, why do we use K? Because it tells us, it lets us know, like I said before, which reaction is favored. Is it the forward reaction, all right, or the reverse reaction? Think about it. If the forward reaction is favored, what are we making more of? Reactants or products? Products, right? Because you're going forward, left to right. Okay. If the reverse reaction is favored, which are you making more of? Reactants. Now it is all right here as well. All right. If K equals 1, okay, if K equals 1, our reactions are at equilibrium, meaning the forward reaction, you're producing products at the same rate you're reproducing those reactants. All right? So you're at equilibrium. If K is greater than 1, the reverse reaction is favored and you have more reactants. All right? K is less than 1, the reverse reaction is favored, and you have more reactants present. All right. And lastly, if K is greater than 1, the forward reaction is favored, and you have more products. Now think about it in terms of numbers. If your reactants are favored, where are they in your equation? Bottom or top? So if they're favored and you have more of those guys, it should make sense that, hey, since it's on the bottom here of this reaction, if I have more of those, all right, my K has to be less than 1. Think about it. 1 over 2 is less than 1. It's 0.5. 1 over 3, 0.3, and so on. Where if you flip it, if products are favored and they have a bigger number, then obviously it's going to be greater than 1. 2 over 1, 3 over 1, and so on. Okay? This last piece right here that's on this slide, this is something that's the most critical when we start to write these equilibrium expressions that we're going to get into here in just a couple minutes. Okay? They only include gases and aqueous solutions. We do not use solids or liquids in terms of our equilibrium constant because they don't have a concentration. Okay? Concentration, guys, implies somewhat of a mixture. Right? Aqueous solutions. You took a solid, you mixed it with maybe water or some other solvent. Now we have a concentration. That's how we can measure them. So based on our rate of reaction, it depends on how much we have of a substance. So if we can't measure concentration, we can't know, or they can't have any impact on our equilibrium constant. Okay? So you can't forget that. I highly recommend that you guys make flashcards for these values. All right? You will see a question related to equilibrium on your final exam. Okay? Every year they put one on there. They may say, well, if K is less than 1, which reaction is favored? And you have to know what it is. Okay? So I would encourage you to take 3 flashcards, or make 3 of them. K equals 1, on the back put equilibrium. If K is less than 1, put reverse, more reactants. Another one, K greater than 1, forward, more products. You have to memorize, you've got to know these. Find some way to remember them that works for you, and then remember that, hey, it's only gases and aqueous solutions. Questions so far? All right, moving on. Here's our first example. We need to write the equilibrium expression for this reaction. We've got nitrogen plus oxygen, all right, and it yields 2 moles of nitrogen monoxide. Okay, so what is our general expression for the K? K equals blank. Products over reactants. So, how many products do I have here in this reaction? 1, what is that product? NO. So, I'm going to put that on top of my fraction. I've got NO and its concentration. How do we show concentration, Dallas? Oh, you weren't even paying attention. Brackets. Okay. Now, what else does NO have right there, guys? Coefficient. What do coefficients represent? Number of moles. Good. It's a little review there. Now, this is something you got to remember, guys. Coefficients, they're important. Subscripts, they're within the reaction. They're within the formula. Okay? They're not going to change. This is not the first time we've seen that, right? We have changed or can change coefficients when we balance equations and things like that. It's those subscripts that never change. So since we can change our coefficients because we can change the number of moles, we have to include them in our expression. Right? They're important for some reason. So they become exponents, guys, or superscripts. All right? So it's going to come to the end of this and it's become an exponent, a superscript. All right? Then on the bottom, are those all my products there? All right, so now my reactants. Let me ask you this. Do you think I'm going to have one large concentration for both of my reactants? Or do you think they're going to have individual concentrations? Yeah, they're going to have individual, guys. So when we write them in there, N2, end the bracket. And now instead of adding like we do here in our reaction, we're multiplying their values together. All right, so it's O2 times, the concentration of oxygen times the concentration of nitrogen. That's it. That's the end of the problem right there. That's how you write an equilibrium expression. Or do we have any numbers that we can actually calculate K here? No, we don't. Okay. If you were given numbers, that's when you guys would just plug them in. Well, you'd have to be given the concentration of nitrogen monoxide, given the concentration of nitrogen gas and oxygen gas, then you could plug it in once you have your expression. But if they don't give it to you, this is all you have to do. It is that simple. Okay? Don't overcomplicate it. What I want you guys to do right now, there are 5 in your next note page. I want you guys to go through and try writing the equilibrium expressions for those 5. All right, so take a few minutes and do that. Oh, already the answer up there. When we take a look at these, again, products over reactants, who can tell me what my K expression is going to look like? To be K equals what? What's on top? Products, so in this case it's CO2. So an exponent of 2, right, because it's got that coefficient right here. On the bottom we're going to have Now, do you think it matters, guys, the order of these two right here? No, it does not matter, because why? Because they're multiplied, okay? Absolutely. Kind of looks like a smiley face there. Really weird looking. All right. Now, this next one. Who can tell me what the expression here for K would be? Anna, you take a shot at it? That's it? So you said it's this right here? How in the world are you getting that? Exactly. It's only gases and aqueous solutions. This is the correct answer right here. These solids, you're not going to use because they don't have a concentration. My hat's off to you, Anna, that you had the confidence to go with that when most people would probably put the reactants down on the bottom. Absolutely. So remember, guys, I pointed it out. I said, this is the one thing that people forget the most. It's only gases and aqueous solutions. These are the ones that have concentrations. Liquids and solids do not have a concentration. Excuse me. So, you cross them out. If you see a liquid, if you see a solid, just cross it right out because it's not going to show up in your final expression. Okay? So this is, even though it looks weird, this is your equilibrium expression right here. So will there ever be a case where the reverse reaction is favored here? No. All right, because it's always going to be in the forward direction, because it's always going to be greater than 1, unless your concentration was less than 1, but I don't foresee that happening. Here we go. Letter C, guys. I'm going to go through the rest fairly quickly. All right, so this one should look like this. You've got SO3 on top. It's going to have a SO3 exponent 2. On the bottom, we're going to have SO2 squared, concentration of oxygen. Questions with that one? All right. Letter D, K equals HCl on the top, squared. On the bottom, you're going to have Cl2 and H2. Again, it doesn't matter the order you put those in. Typically speaking, guys, you're going to see them left to right, but just for the sake of an example here, you can switch them. It doesn't matter because, again, they're multiplied. All right, and the last one is E, K equals NH3 on top, and that's squared all over concentration of nitrogen times concentration of hydrogen cubed. All right, questions there? Now let's say, for example, we have some numbers. Okay, so let's plug them in. Let's say we have, 1.5 is our concentration here. Let's say it's 2.3 here and 4.4 here, something like that. All right, how would you solve it? Tell me, you guys go ahead and solve this and tell me which reaction is favored. Take a couple minutes and do that. When we plug it in, guys, it should look like this. 4.4 squared all over 1.5 times 2.3 cubed. Now, again, order of operations. You got to do your exponents first. So you'd have to do 2.3 cubed, then multiply it by 1.5. Okay, so do that out. If we take 4.4 and we square it, what do we get for an answer? 0.06? No, 4.4 squared. 19.3. Okay, then 2.3 cubed, do that. Multiply it by 1.5. Tell me what our new denominator is going to be. Now do the division. 19.36 divided by 18.25 should be 1 point something. 1.06. Dot, 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 dot. Which reaction is favored? Oh, I hear both. Let's go back and take a look. Let me go back a few slides. We said that if K is greater than 1, the forward reaction and more products, because our products are larger, guys. And take a look at this reaction when I get back to it, right here. Okay, this is bigger than this. That means the products are favored. That forward reaction is going to be favored as well. Okay, now, will you see something like that on your final exam? I don't know. Okay, in the past, I don't think they have had you solve for that. But if they do, they're going to give you the concentrations, and you guys just have to plug it in. They will definitely, most likely, ask you for the K expression in some way. Okay? Whether they say, okay, if the forward reaction is this, blah, blah, and then you have to figure out what the K expression is. Alex, did you have a question?